Vectors in 3D. So this is an extension of vectors in 2D and just adding in a third dimension. So we're going to be adding in a z-axis. So let's draw up our x-y axis, but imagining it on a flat surface this time. So x and y axis here, and adding in a z-axis in this direction here. Let's go ahead and just draw out a cube in the 3 dimensions, with the bottom corner being at the origin. So drawing out this cube, we're going to make the cube of side length 3. We're going to get something like this. Now, referencing coordinates in 3 dimension, this will have coordinate of 3, 0, 0, this point here, because it moves along the x-axis 3 units, doesn't move along the y-axis, and doesn't move along the z-axis. Labeling a few more points, this would be 3, 3, 0. This would be 3, 3, 3. This would be 0, 3, 3. And this would be 0, 0, 3. Let's go ahead and draw some vectors in. Let's call this one point A and this one point B. So let's go ahead and draw the vector from O to A. And let's draw in the vector from O to B. And let's draw in the vector from A to B. So this point being O. Now, the vector from O to A, let's call this vector A. It could be represented as 0, 3, 3, but again, we don't like to write the vector like that. We'd rather write it in column matrix form. So it'd be 0, 3, 3. Or also could be represented in component form using I, j's, and k's. So we'd have 0i plus 3j plus 3k. So in 3 dimensions, we add in another unit vector k, which would act along the z-axis and have a length of 1. And obviously 0i doesn't even have to be written. Which would mean that OB, the vector from O to B, let's call it B, could be written as 3, 3, 3 in column matrix form, or 3i plus 3j plus 3k. And just like in 2 dimensions, vector OB is just the resultant vector of OA, then A to B. So we could say, let's write up an equation to describe that. So we can say the vector from O to A plus the vector from A to B is the same as the resultant vector from O to B, which means that vector AB is just vector OB minus vector OA, doing a bit of algebra. And we can go ahead and just grab the component forms of those and subtract them. So OB is 3i plus 3j plus 3k minus OA, which is just 3j plus 3k. And doing that is just going to give us the vector 3i, which should hopefully make sense because there's no movement along the y-axis or z-axis here, so it makes sense that that vector ends up being 3i. We can also find the magnitude of a vector in 3 dimensions. So let's go ahead and find the magnitude of that vector. And the magnitude of a vector in 3 dimensions is just using Pythagoras in 3 dimensions. So we can say it's the square root of x2 minus x1 all squared plus y2 minus y1 all squared plus z2 minus z1 all squared. And in this case, we can do that. Well, let's find the magnitude of, let's go ahead and, well, the magnitude of AB in this case is just going to be 3, but let's go ahead and find the magnitude of OB. So in this case, we're going to have the square root of 3 minus 0 all squared plus 3 minus 0 all squared plus 3 minus 0 all squared, which is just going to be the square root of 9 plus 9 plus 9, which is the square root of 27, which is 3 root 3. So it's the magnitude, the length of OB. If we wanted, we could then find the unit vector in 3 dimensions as well, because our unit vector of OB, let's call it OB hat, is just going to be the vector OB over the magnitude of OB. And in this case, we're just going to get 3i plus 3j plus 3k all over 3 root 3. And we can divide each of those individually. So 3 over 3 root 3, we're just going to get 1 on root 3i plus 1 on root 3j plus 1 on root 3k. And if we rationalize the denominator there, just timesing each of those by root 3 on root 3, we'll have root 3 on 3i plus root 3 on 3j plus root 3 on 3k for the unit vector.